Okay, Assalamu alaikum guys. This is the last part of waves. We will be talking about electromagnetic waves. We will be talking about light. Yes. What is the speed of light? So the speed of light travels at 300,000 kilometers, not per hour, per second. Isn't that mind-boggling?
Yeah.
C equals, that was my son by the way, 300 million meters per second. To me, this is really mind-boggling. 300 million meters per second, that's a lot. I mean, I wish I could do just 300 meters per second, like the speed of sound, V of sound, is 343 meters per second. Can you see that there is like 343 and the 300 basically the same, and you could see that there is a factor of 1,000,000. So the speed of sound is 1,000,000 bigger than the speed, the speed of light is 1,000,000 bigger than the speed of sound. Isn't that amazing? I find that, I could ruminate over this for days and days and days. It's just amazing. 300 million meters per second. Imagine if you were light and you traveled 300,000 kilometers in one tiny, weeny little second.
That would be so fun.
Okay, so light, so we said that the speed of light is 300,000 kilometer per second, or 300 million meters per second, but we are old enough to write it as 310 to the power of 8 meter per second, or 310 to the power of 8 meter second minus 1. This is what the IB prefers, but it doesn't matter. Meter per second is fine too. So all the electromagnetic waves, all of them, they have this common speed that is 300 million meters per second. Okay, so let's take a look at the electromagnetic spectrum here. The visible light is this tiny part of the huge electromagnetic spectrum, and you've got infrared, you've got microwaves, radio waves, long waves, you've got ultraviolet, X-rays, and gamma rays. So the visible light, we have red at 700 nanometers, and we have blue or violet here at 400 nanometers. I'll come back to what nanometer means in a little bit. But for now, what I want you to see is that the C is the common speed for all these electromagnetic waves, and then you've got C equals lambda F. So from this here, C is constant, it doesn't change. For in vacuum it's 300 million meters per second, and then you've got lambda F. I want you to look at this relationship. So C is constant. So if I give you lambda and then I ask you for the frequency, how would you go about that? I give you the lambda, and then I ask you to go to find the frequency. So we have C equals lambda F. Then you divide by frequency here. No. This is, I give you the lambda, and then I want you to find the frequency. So you're after the frequency. So C equals lambda F. I'm after the frequency, so I need to get rid of the lambda here so as to isolate the frequency. So lambda and lambda, they cancel out. Goodbye. Okay, and then you've got the frequency equals C over lambda. You see here, guys, F and lambda, they are not upstairs. F is upstairs, lambda is downstairs. If I look for lambda, I will have also C over F. So what is this kind of relationship again? We talked about it. This is an inverse relationship. So F and lambda for light, for the electromagnetic waves, because the C here is constant, what happens to them? They are inversely proportional to each other. They have an inverse relationship. That means what? That means if you have here long waves, you have long wavelengths, but here you have very short wavelengths. So in the long waves, you will have smaller frequencies compared to the very high frequencies here for gamma rays and X-rays and ultraviolet light. So when the frequency is high, the wavelength is short or small. When the frequency is small, well, it's 1,000,000 hertz, that's huge, you know. 1,000,000 hertz means 1,000,000 cycles per second. That's still, you know, to me, you know, like huge. But then in comparison with the gamma rays which sit at 10 to the power of 20, you know, these radio waves have shorter or have smaller or have, you know, a less of a frequency. But then the wavelengths here are much longer than the wavelengths here. So, and then you've got to see this inverse relationship between the frequency and lambda. That is of crucial importance to know that gamma rays, they have the highest frequency and the shortest wavelength, while the long waves here have the least frequencies and then the longest wavelengths, up to a kilometer here, 1,000 meters, 100 meters, 10 meters. But here we're talking about nanometers and even angstrom, and I'm gonna explain talk a little bit about that. Okay, so for prefixes, you know, I know that so many of you struggle with these, that's why I'm gonna talk about them. So if you see the prefix kilo, kilo means 1,000, 1,000. Kilo, any kilo of anything, kilogram means 1,000 grams, kilometer means 1,000 meters, and so on. So now, we are not talking about these, we are talking about what is a centimeter. A centimeter is going to be 1 part over 100 parts. So you take that meter and you divide it by 100, it gives you that tiny part is a centimeter. And so we could write it like this, 10 to the power minus 2 meter. You see that this guy here is just 10 to the power of 2. Then 1 millimeter, so you take that meter and you divide it by 1,000, okay, 1,000 here. So that is 1 over 10 to the power of 3. When it goes upstairs as 10 to the power negative 3 meters. That is millimeter, millimeter. Then if we go a little smaller, I am not interested in 1 part of in 1,000. I'm interested in 1 micrometer. What is 1 micrometer? 1 micrometer is 1 part over 1,000,000. It's 1 part over 1,000,000. So it is 1 over 10 to the power of 6 and 10 to the power negative 6 meter. When I take the 10 to the power 6 here upstairs, it goes as 10 to the power of negative 6. If we had like a mega, 1 mega, the mega is 1,000,000, 10 to the power of 6. But the micro is 10 to the power of negative 6. So it is 1 over 10 to the power of 6. Now we reach the nanometer. I'm sure all of you heard about nanotechnology. Okay, so nanometer is 1 part over what? Not 1,000, not 1,000,000, but 1,000 million. So what is that? A billion. You got that. So that is 1 nanometer. 1 nanometer. So I'm gonna erase this, and then I'm gonna talk about the nanometer, and I hope that it stays with you, you know. In my time, we would not be given any formulas, any calculators, or a nanometer, we just needed to know what a nanometer was. We needed to know what an angstrom was. We needed to know all these prefixes by heart. Okay, but that's not the case now, and it's okay. 1 nanometer is 1 over 10 to the power of 9 9, okay, meter. Okay, so if we were talking, let's say they give you a wavelength and then they say, oh, lambda equals 300 nanometer. So where would that fall in the spectrum here? The visible, it goes from 700 nanometer towards 400 nanometers. So 300 nanometer would be sitting here in the ultraviolet. So, and then they tell you, oh, can you find the frequency? Can you find the frequency for that electromagnetic wave? I'd say, sure, super duper easy. C equals lambda F. F and lambda have an inverse relationship. F is going to be C over lambda. I choose 300 nanometers because it's going to be very easy for me to do the calculation without using a calculator. So what is the value of C? You memorized it by now, right? 10 to the power of 8 meters per second. Lambda, I chose this lambda, 300. If I just write 300 nanometer like that and then do the calculation, well, my teacher would give me a 0. Nanometer is 10 to the power negative 9, okay, meters. And then so the meters here and the meters here will cancel out, and then you will have 1 over S or hertz. Okay, so what is 300? 300, can we write it as, okay, 300 is just 10 to the power of 2, 10 to the power negative 9. Lath, please don't say this is complicated because it's super duper easy. Okay, so 3, here 2 and negative 9, it gives me negative 7, and here 10 to the power of 8. This negative 7, when it goes upstairs as 10 to the power plus 7. I can get rid of these 2 3's here, the 3 here and the 3 here, and then 10 to the power of 8 times 10 to the power of 7, and it gives you a 10 to the power 15 hertz. That is something, you know, like I just 10 to the power of 15. Can you ruminate over this? This is like this is 8 plus 7 is 15, right? So 10 to the power of 15 hertz, that's really, that's a lot. That's a huge frequency for me. It's just, you know, I cannot imagine it. I can maybe imagine frequencies of a cup of maybe 100 hertz maybe, but other than that, it's just too much. So I hope that the story of nanometer became easy for you. Then take a look at the gamma rays. You know, the wavelength of a gamma ray is 0.1 angstrom, is around, it is an angstrom. And an angstrom, we put a small 0 on top of the A, is one part, is a tenth of a nanometer. So 1 angstrom is 0.1 nanometer. This 10 here is 10 to the power 1. When it goes upstairs as 10 to the negative 1, 10 to the negative 9, so it is 10 to the negative 10 meters. So if 1 nanometer is 1 over a billion meters, it's so small, the angstrom is a tenth of the nanometer. You take that nanometer and you divide it by 10. And 1 part is going to be an angstrom. So that's very, 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 very small distance. So that would be the length of the wavelength that corresponds to the gamma rays. However, the frequencies of the gamma rays, X-rays, ultraviolet they're much, much higher than those of the visible light, and even higher than those of infrared, microwaves, radio waves, and long waves. So I hope that you see the inverse relationship between frequency and wavelength, because that is important too, not just for your exam, but in general. You know, you're going to be a future engineer, future thinker. Now you're thinking, so maybe a future engineer. You really need to know that frequency and wavelength have an inverse relationship, especially in the electromagnetic spectrum, where the C is constant, the speed is constant. So the C is constant for the whole electromagnetic spectrum. What else did I want to tell you about? There are so many things to say here, but basically that's what I want you to know. Okay, yeah, frequency and energy. Frequency and energy. You know, frequency and energy are two faces of the same thing. Frequency, the higher the frequency, the more energy. So in this spectrum here, which waves are the most energetic? When you just take a look at this spectrum, which electromagnetic waves are the most energetic? And as my son always says, gamma rays can kill you, gamma rays can kill you. So gamma rays, you guessed it. So their frequency is about 10 to the power of 20. That's very, very high frequency, and therefore they have lots of energy, and they're very, very energetic. The long waves, they have the least frequency, and then they have the least energy. The wavelength here is like 1,000 meters. That's 1 kilometer. Can you imagine a wavelength? You know, like half of that wavelength is half a kilometer. Yeah. So okay, if you listen to radio and you listen to FM here is going to be around 100 megahertz. What's mega again? Mega is 10 to the power of 6, and 100, so that would be 10 to the power 2, 10 to the power of 6, 10 to the power of 8 hertz. I'm telling you guys, anything beyond 100 hertz for me is just like dizzying. Okay, so this is 100 megahertz. That's the FM. Okay, FM. And so this is it. You know, energy, frequency are about the same thing. Wavelength is lambda equals C over F. The higher the frequency, the shorter the wavelength. Okay, you got it? And when you got it, you got it. Okay, I'll talk to you in